Hello, Bobcats. This is Chemistry 2341. We're going to continue on with Chapter 9, Nuclear Magnetic Resonance Spectroscopy and Mass Spectrometry. And this is Section 1, which is the Introduction to NMR, or Nuclear Magnetic Resonance Spectroscopy. Okay, so in this introduction, nuclear magnetic resonance spectroscopy characterizes organic molecules by identifying the carbon and hydrogen frameworks within molecules, okay? We're going to use two types of NMR spectroscopy, although there are other types. We're going to use what we call proton NMR or hydrogen NMR to determine the number and type of hydrogen atoms on a molecule. And we're also going to use an isotope of carbon or carbon-13 NMR to determine what types of carbons we have in a molecule. Okay, so in NMR, we use radio waves to pulse the nuclei of the different atoms to sense where they are and what the electronic structure is around them. And as such, when we use these low energy radio waves, they react with just the nuclear spin. And when we interact with just the nuclear spin, we can look at the proton of a single hydrogen atom or the mixed protons and neutrons in a carbon-13 atom. Okay. Notice that only nuclei that contain odd mass numbers or odd atomic numbers give rise to NMR signals. This because you need a mismatch of hydrogens and protons and neutrons in your nuclei to get this spin to appear in the NMR. Okay, so there are four most important things about proton NMR, okay? We're going to look at the position of a particular proton or hydrogen as it absorbs, and that is determined by its electronic environment. And we're going to look at that chemical shift. That chemical shift is the position on the NMR, and it's typically measured in ppm or parts per million. Whenever we look at an NMR, we have a proton NMR in particular, we have four things we're looking for. Number one is the number of signals we have. Number two, the intensity of those signals. Number three, the position of those signals or chemical shift. And number four is the spin-spin splitting or coupling of those signals. I'm going to go through each of these one by one and show you how to identify them and why they're important. Okay. So let's just back up and start with what a general NMR spectrum would look like. An NMR spectrum is typically a plot of the intensity of the peaks against the chemical shift of the peaks. And again, that's measured in parts per million as we shift along the x-axis here. So if we look at this one right here, our number one is our number of peaks. And in this compound here, we have one peak for one of the hydrogen types and one peak for the other hydrogen type. This peak right here is our standard, and I'll talk about that in a minute. And occasionally we see a little bit of our solvent in our system as well. But these are the two peaks we are interested in and to help us identify the compound we are analyzing, okay? So the next thing we want to look at is the intensity. Notice the height of these peaks. That is measured on this Y scale, the intensity of those peaks, okay? Now the position is the shift along this x-axis. Notice this one is somewhere between 1 and 2, and this one is somewhere between 3 and 4. That is our shift we're talking about. And notice that these peaks are split into a group of 4 peaks, and these peaks are split into a group of 3 peaks. That splitting becomes important as well. So those are the 4 things we're looking for in our standard NMR spectrum. Okay, so in proton NMR, the NMR absorptions generally appear as sharp peaks. Occasionally they don't if there's something like hydrogen bonding involved. Okay, the chemical shift increases from right to left. So we start at 0 and we move up downfield. Okay, the term upfield means closer to 0. The term downfield means further away from 0. And so those are just relative terms that you can use when describing 2 peaks. Okay, NMR absorptions are measured from a relative position based on a reference standard. Our reference standard is typically tetramethylsilane. For both proton and carbon NMR, we tend to use that as our zero as a zero chemical shift on both proton and that carbon NMR, and everything is typically shifted downfield from that, okay? All right, so now let's talk about number of signals, okay? The number of signals you get in an MR equals the number of different types of protons, not the different hydrogen, number of hydrogens, the different types of hydrogens you have in that compound, okay? So protons in different electronic environments give different NMR signals, okay? So let's look at these compounds here and look for equivalent and non-equivalent hydrogens or protons. Okay, if we look at this compound here, we see we have a carbon with 3 hydrogens on it and it's bonded to an oxygen, okay? So that means it has an electronic environment that has that oxygen, a carbon, and 3 hydrogens. Let's look at on this side here, we have a carbon with 3 hydrogens on it bonded to an oxygen, okay? So they have equivalent electronic environments and therefore they give one NMR signal, okay? In the next compound here, we have a carbon that's bonded to a carbon and a carbon and it's also bonded to a chlorine. So that gives it a electronic environment of having a carbon and a chlorine bonded to that carbon. So these hydrogens have a unique signal, okay? Now we have this carbon that has 3 hydrogens on it and only bonded to a carbon, okay? That gives it a different electronic environment and therefore these hydrogens are different than these hydrogens because the absence of that chlorine bond. Therefore, we should see 2 signals for that compound, okay? Now, the differences can be even a little more subtle here. Let's look at this group right here. We have a carbon with 3 hydrogens on it bonded to an oxygen, okay? So that's gonna give us 1 signal. We now have a carbon with 2 hydrogens on it bonded to an oxygen and a carbon. So that's going to give us a different signal than the one with the 3 hydrogens on it. So this is going to give us our second unique peak. And then we have a carbon at the end here with 3 hydrogens on it bonded only to a carbon. So that's going to give us our third unique peak. So in this compound, we have 3 different peaks in our system, okay? Now, when we have rings or double bonds, make sure you draw out where all the hydrogens are, because if you are not paying attention, you could miss out on knowing whether they're equivalent or non-equivalent. For example, in this structure here, this looks like they might all be equivalent, but let's go ahead and draw it out and show you why it's important, okay? So when we're looking at rings or double bonds, we have to think about where the hydrogen is compared to the thing that it can be electronically interacting with it. So in the case of this first compound here, we have a hydrogen and it cis to a chlorine and it goes through these chemical bonds. We have this hydrogen that is also cis to chlorine and still goes through those chemical bonds. Therefore, those are equivalent hydrogens. They have the same electronic environment, okay? Now let's look at this compound here. The difference here is now we have a chlorine and we have a bromine here. So that means that this is going to be cis to a chlorine, and that's going to have a different electronic environment than the being cis to a bromine. That means we're going to have 2 signals for these hydrogens because of their different proximities to different atoms, okay? Now let's look at this last one here. We have 3 hydrogens and only 1 chlorine on our double bond here. So we have one that's cis to this. That's going to give us 1 signal. We have one that's on the same carbon with the chlorine. That's going to give us a second signal. And we have this one that is not cis to or close to the chlorine at all. That's going to give us our third signal. So in this one, we're going to have 3 different signals. So you really have to look for the equivalent hydrogens to make sure how many signals you will have. All right, now let's look at a ring here at the bottom, for example. If we look at the just cyclopropane that's unsubstituted, the top and the bottom are the same. They're all seeing 2 hydrogens each, and therefore they all have equivalent number of peaks, and therefore we get 1 signal for this material here. Just by substituting one of these hydrogens for chlorine, we now have the 2 on the top here are going to be close to the chlorine. That's going to give rise to 1 signal. We have these 2 over here that are far away from the chlorine. That's going to give rise to our second signal. And we have the chlorine, the hydrogen here that is on the carbon with the chlorine. That's going to give us our third signal. So just that single substitution on that ring gives rise to a total of 3 different electronic environments and therefore 3 different peaks. Okay, so let's talk about the position of the signals. The electron density near the nucleus shields it from the magnetic field. So the more electrons you have on there, the more it is shielded from the system, okay? The less shielding, the less shielded the nucleus becomes, the more it feels the magnetic field and the spins are interacting with it. Therefore, deshielding shifts the nucleus absorption to a higher frequency or down field. So if you can think about it, if electrons are being pulled away from the carbon with that hydrogen on it, it's going to shift it down field, okay? So if there's very little electron withdrawing on that hydrogen or on the carbon that those hydrogens are, there's going to be less deshielding, and it's going to be shifted upfield from the other ones. So protons near electronegative atoms are deshielded, and therefore they are going to be shifted down field. Okay, let's take a look at, see what that kind of means, okay? So let's just look at this one for our positions here, okay? So if we look at this compound here, we have hydrogens that are a total of 2 bonds away from the bromine, and these hydrogens that are 1 bond away from the bromine. The hydrogens that are on 1 bond away from that bromine are more influenced by the idea that the bromine is electron withdrawing. Therefore, those hydrogens are more deshielded than the other hydrogens are, which means they're shifted more downfield than the ones that are further away from the bromine, okay? So this is also affected by the different type of atom you have. So in this case here, it's similar to what we have with the bromine system, where the hydrogens that are on the carbon next to the chlorine are shifted more downfield than the ones further away, okay? Because in this one right here, because fluorine is more electronegative than bromines, these are going to be shifted more downfield because they're having more electron density pulled away from them, so they're more downfield. And in the case of this last example here, we have hydrogens right here, and it has 2 chlorines on this carbon, and these hydrogens have only 1 chlorine on the carbon, which means if there's 2 chlorines pulling electron density away, that these, the one that's on with 2 chlorines on it is going to be shifted further downfield than the one with just 1 chlorine on it. So we should be able to tell them apart based on that shift on whether or not it's downfield or upfield from the other peaks. Okay, so where do we expect to see this based on what functional groups we have? So in this chart, it gives you an idea of what we have. And the first thing I'm going to look at is I'm going to look at the hydrogens on electronegative atoms, okay? The hydrogens on electronegative atoms like alcohols, amines, and the phenols here, they can hydrogen bond, and they are bonded directly to a electronegative atom. And so they are going to be, number one, fairly broad in range and fall somewhere between, with alcohols and amines, between 1 and 6, and in phenols somewhere between 4 and 8. Okay. Now, the next most common thing we have here is just your aliphatic hydrogens here. Anytime they're primary, secondary, or tertiary and just bonded to a carbon with only sp3 hybridization, we're going to see those down here at the lowest number, most upfield of any of our protons we'll see. And so then once we get next to items that start pulling electron density away, like double bonds, aromatic rings, carbonyls, or triple bonds, those start to shift downfield, okay? So those are shifted between 2 and 3 ppm, okay? Now, if the hydrogen is on a carbon bonded directly to an electronegative atom that's pulling more electron density away from it, those are shifted between 3 and 4 ppm, okay? Now that we have, the next thing up we have is hydrogens bonded directly to a double bond, bonded directly to an sp2 hybridized carbon. Those tend to be shifted up between 4 and 6.5. Once we get to benzene, the conjugation gives us a little bit more of a tug, and therefore we're higher. We're in the 6 to 8.5 range. And then once we get to carboxylic acids, number one, it's broad because of hydrogen bonding, but it's bonded directly to an electronegative atom that's bonded directly to another carbon with another electronegative atom. And in the case of aldehydes, we have that hydrogen bonded directly to a carbonyl, and those two hydrogens are shifted up the highest in the most common range, which is just right around 10 or just above, up to approximately 13 parts per million. Okay, so what we'll see here is this is a table summarizing those results, looking at the alkyl groups are the lowest shifts, shifted most upfield. And then as we start getting electron withdrawing groups closer and closer to those hydrogens, we see them slowly starting to shift downfield until we get to ones that are bonded directly to carbonyls, like the aldehydes and the carboxylic acids, which are shifted the furthest downfield possible. All right, and that concludes our introduction to proton NMR.